So raise your hand if you have an iPhone. Okay, so all you guys, all these years of using an inferior technology is finally going to pay off in comparison to Android, because what is the feature that the iPhone 8 has that the other iPhones don't have? A 3D camera. So 3D technology is becoming ubiquitous. It's all over the place. And what I want to show you in some of the work I'm doing is something that we've been working on for 7 years. I didn't make much progress for about 6 of those years. And since everything's changing in machine learning, we've made dramatic progress in the last year. What does that have to do with DXA? It's because a lot of what we do in body composition, it can't be done unless you advance the body composition models of DXA as well, so that you can use it as a more effective tool for accessible technologies like optical. So nothing wakes up an audience like a slightly overweight, middle-aged man in his underwear. So I'm going to use myself as an example that's going to get you to the end of the talk right at the beginning, and that is that we can build models from these optical scans and predict what a person will look like with a change in a fat mass or lean mass or a visceral fat or even age from the models that we derive. And I'm going to give you an example of myself. We start off with myself in the middle, the BMI of 28, and this model is used to show that if you go to the left, I've reduced the weight of 20 kilograms in the model, and you can see this is Buck John with 40 pounds less fat, and if I gain 40 pounds of fat from where I am, that's obese John with a BMI of 33. You can see this is a different phenotype. You can see the difference in the scans from when Buck John's looking pretty good. And that's from the way the data drives a model, the way a man takes off fat and the way a man puts on weight. And you can see how much of the adiposity goes on there. This is an increased muscle mass of 20 kilograms. And you can see that gives you bodybuilder John, which has decrease of 20 kilograms of fat and an increase of 20 kilograms of lean, which is the same BMI as I am now, but you see quite a different phenotype. Or if I just increase lean from where I'm at, it's bouncer John, and if I increase fat and lean, it's linebacker John. But what is most interesting here is if you decrease muscle mass by 20 kilograms of my current model, and that gets me into a model that is effectively a sarcopenic John, where it has a decrease of just about over 80 pounds with a loss of 20 kilograms of fat and 20 kilograms of lean. This middle one is probably a never sports John, where I have the same fat, but not just I have about 40 pounds less muscle than I have now. And then here's the decreased muscle and the increased fat, which you can see looks like a sarco-obese phenotype just by visual inspection of that image. Now, the beauty is that these are models from the data. You can take an image like this and go backwards as well. And that's what I want to do in the rest of my talk, is show you how to do that. So this is the simple outline. Why DXA is great, why DXA is not so great, and solutions to the not so great part. So DXA is a broadly available tool. As most of y'all know, it's a gold standard for bone densitometry. It's been around for body composition since the same time it did bone density. The patents that are used by Hologic to measure body composition are my patents. So this is something if I don't know anything else, I know something about DXA. And the output measures are, fat, lean, and bone. I'm going to show you how you can also derive body volumes off very accurately and precisely. And you get all these measures with arms with segmented values, which is quite difficult in other technologies. And some of the new systems out, you can see here's a unit that's by Norland that can do individuals up to about 625 pounds. The other systems by GE Hologic can go all the way down to 1 kilogram for little neonates. So it's a very effective technology that starts off with these two low and high energy images, and using its most fundamental principles, it can only give you 2 pieces of information, and that is bone and soft tissue. But DXA is most known for its 3-compartment model, and this is done by, I'm not going to go through all the derivation, I'm just going to call it DXA magic. And if you take those 2 high and low energy images and you apply some DXA magic, you get your bone mass and soft tissue mass. You can go a step further with some DXA magic and divide that into fat mass and lean mass. The physics is not really important here in terms of the segmentation of the algorithms, but you ultimately can end up with fat, lean, and bone using the idea that you can always measure two things, and if you know that the pixels don't have bone in them, that gives you fat and lean capability, and then you can interpolate over the bone. That's the DXA magic. And you end up with something like this. These are not the images that you standardly get off a DXA image. These are what my group create, which are full images of either bone, fat, lean, or percent fat. And once you can do this, it enables you to do all sorts of things. It's very precise. If you look here, looking at the precision and test-retest precision, and this is a long-term precision that's measured on an average. I think this data set was over 15 days. You get about 500 grams of precision for fat, 700 grams for lean, and about 0.6% for percent fat. So your ability to monitor change over time is higher than other technologies because of this high precision. And in this paper, the precisions for each one of the subregions was also calculated so that you could follow changes in any region you're interested in. And with the NHANES reference data, you have an exceptional capability to get expectation values by sex, ethnicity, and age. And that's from 5 years, on NHANES it's down to 7 years old and up to about 85 years old. Visceral fat and subcutaneous fat is going to be released in about 2 months. So you then will have that same power to look at visceral fat across the U.S. population as well. You can also monitor rate of change in the reports by looking at each of these values and looking at statistically significant changes over time. So there's a lot of good things about DXA. It's broadly available, measures these great measures, it's precise and accurate, and has these subregional changes. But DXA is also not so great in some ways. And this is the paper that really changed things for me, and this was a paper by Newman that came out in 2006, and it really just kind of, as being a DXA guy at the time, it kind of changed everything, and that was that in the Health ABC study, if you looked at the odds ratio for predicting mortality using strength, either quadriceps or grip strength, it did pretty well. It had a significant, unadjusted hazard ratio here for men and women. It was significant for both. But if you adjusted it for body composition, which you think it would go down, but it didn't go down at all. So it meant that, the body composition didn't really take away any of the power of explanation of mortality from strength. And if you did the opposite of looking at either CT cross-sectional area or DXA of the legs or arms, CT cross-sectional area did a little bit better than DXA, but DXA just didn't show anything at all for mortality. So this really changed the way I looked at lean mass. If it didn't predict mortality, there's something wrong. So why is lean mass not muscle? There's several things to take into consideration. One is that when we're thinking of muscle, it's a tissue compartment like adipose tissue or bone, and it has molecular compartments of each of the 4 compartments in the body: water, lipid, protein, and mineral. Adipose is primarily lipid, about approximately 72%. But it has this other lean tissues of water and protein as well. So if you took out a chunk of adipose tissue, it's going to have lean mass in it. Muscle's the same way. Muscle has lipid in it, approximately 5%. It's primarily water and protein. So when you use DXA and look at and bone the same. Huh. Oh, that's me. Oh, I thought that was the. Oh, okay. Accidentally recorded something on there. Sorry. Part of a course. Anyway, so bone also has components of each one, but it's primarily mineral. So if you measure the DXA compartments of fat and lean and mineral, you're not measuring just adipose, muscle, and bone. You're measuring fractions of each one of those. And that's part of the limitation of DXA, is that if somebody puts on adipose tissue, they're going to put on lean mass just because it's adipose tissue has lean mass in it. So why is lean mass not strength? Well, strength is, I'm not going to dwell on this because it's been talked about all day, but the things that I wanted to talk about that are potential error sources in DXA because the effort I can't do anything about as a data scientist, muscle units I can't do anything about, mitochondrial count and your capacity for energy utilization I can't really do anything about. But there are some errors that people don't take into consideration that need to be explored, and that is extra osseous mineral content change with aging. If you have the slightest increase in mineral in the muscle as you age, and we know that's true in other tissues like the breast, many more calcifications in the breast, these are just benign calcifications, occur as a woman gets older, and if that similar process happens at any degree in the muscle is going to look leaner than it actually is. So it means that DXA lean would look very different than maybe cross-sectional CT area because of this artifact of mineral. Functional protein, the water ratios may change as well, and this could be due to hydration effects as we get older. And DXA is not really sensitive to those two things. So DXA is not so great because it doesn't predict mortality. Lean is not muscle. Lean is not strength. And as other speakers have talked about, it only has a marginal association to fall risk when we would like it to explain all the risk. So what are some of the solutions that we can look at? One, I'm going to introduce a concept called four-compartment DXA, which is trying to separate out the water from the protein with a simplified model. And each one of these volume measurements, shape and appearance models, and translation to optical we'll talk about. So first, DXA four-compartment model. The first time I met Steve Heimsfeld was I was putting on a workshop in Vienna, and I wanted to ask Steve a question for a long time. So I went, maybe if I invite him to Vienna, Austria, I could ask him my question. So he said yes, and I cornered him one day, and I said, Steve, why is it that in a DXA model, and let's get to the in the DXA model, I'm sorry, in the four-compartment model, it uses DXA, but it only uses it for mineral. So let's look at the four-compartment model real fast, which is fat, mineral, protein, and water. It separates out protein and water, which DXA doesn't do. The water is not really considered functional mass. The protein is. To get a full four-compartment model, it takes 4 measurements. But you should be able to pull out protein, and many of you might not be used to seeing protein as a four-compartment, but really if you put it in this way, there's only 1% residual mass of other things like glycogen. But to get this model, you have to do scale weight, you have to do deuterium dilution for water measurement, you use DXA for BMC, and you use BOD-POD or underwater weighing for total body volume. And with those 4 measures, you get the 4 estimates out from the model. So my question to Steve was, DXA's in the four-compartment model. Why doesn't one use the soft tissue information that's in the DXA in the model and make it simpler? And his answer was, I'm not really sure. But the answer, I looked at this for about a year, and I found out it's because you can't do it. You can't pull water and protein out from each other, so it can't simplify it. You've got to do something more. So what we looked at is ways to optimize it. Here's just the Lohmann equation that's most widely used for that. And if you use the current model of the 4 measurements, it takes about 4 hours, and the analysis time is on the order of days because of the deuterium dilution. So what if you could, though, just take a DXA and then do a water measurement? And the hypothesis is that you could use the bioimpedance for a water measurement and use the soft tissue information from the DXA to estimate body volume, because the masses should be related to physical densities, and that should relate to body volume. So the first thing we did is we said, well, what would the equation be, and how do you derive body volume from DXA? And we did this by, we had lots of data, and you might as well, where you have a BOD-POD for percent fat measurements. And if y'all aren't familiar with BOD-POD, it's a pod you sit in that you display, it displays as air, and it measures your body volume very accurately. So many of you might have data sets that have BOD-POD and a DXA in the same data set. So using those, you can derive the 3 measures that you need to solve this equation. The equation is for total volume needs to be estimated from DXA lean mass, DXA fat mass, and DXA bone mineral content. So you've got 3 unknowns here, which are really the physical densities, or the inverse physical densities, And how many people would you need to scan to solve this equation? 3, right? Because you got 3 unknowns. But if you have 1,000 people, you can get better estimates because it averages out the noise. So we did this for both GE and Hologic systems. We derive these coefficients, and you can use this right now. If you want to use this equation with these coefficients, we've validated it across different devices, and it works. You can get very accurate estimates of either total body volume or regional volume. And how you do it is you pick the appropriate equation. If you have a GE or Hologic system, you pick the regional values from the DXA report. They give you fat, lean, and bone mineral. You plug those masses into the equation, and that gives you the volume of that region. What's a practical example? Well, we have a study at UCSF looking at lymphedema in women after breast cancer, and looking for accurate and precise estimates of change in the arm volume. So that's one possibility of how, and how we're using it. You can also derive new indices, and here's an indice that I don't present in fully, but you can see it's the trunk volume to leg volume ratio. And this ratio actually turns out to be a body shape measure that says how big your trunk is compared to your legs. And, you know, in a high visceral fat phenotype,